Mais pour moi, il faut mettre veille.
Pour toi, il faut mettre le réveil. Et aussi que c'est un peu fatigant de participer dans la nuit parce que c'est différent. Si tu ne dors pas dans la nuit, tu dors dans la journée, ce n'est pas la même chose.
Absolument, absolument. C'est vrai. Mais c'est intéressant.
C'est intéressant. J'ai participé la semaine dernière.
Oui.
Et Nguyen m'a dit que si je veux parler, mais je dis que ok, peut-être je vais parler aussi le travail avec toi. Mais c'est un peu topologique, mais pas très singularité. Donc, non, je vais. Pas de problème.
Pas de problème. Non, je crois que ça peut être intéressant quand même. Oui. Oui.
Oui. Ça fait quoi maintenant à Rio Preto?
Oui. Mais il faut mettre le manteau.
Oui.
Mon Dieu. C'est terrible.
Étrange ici. On n'est pas habitué.
Je t'ai dit, bientôt tu pourras faire des bonhommes de neige. Il semble tout le monde dort.
Ailleurs, c'est encore tôt, non? Au Mexique, il est à peine 2 heures, mais bon, c'est l'heure de manger.
Oh, ben alors, bon appétit, Jawad.
Merci.
Bon appétit. Est-ce que tu vas manger cochonito pibil?
Ah non, je ne sais pas encore, je vais voir ce qu'il y a dans le frigo.
C'est très bon, cochonito pibil.
So we continue with our afternoon session.
Je n'ai pas encore appris à préparer ça.
I have the pleasure to introduce Nguyen Thi Bich Thuy from UNESP in São José de Rio Preto, and she's going to talk about a proof of the Euler-Poincaré formula using the Cauchy's method for some well-known surfaces. Thank you.
Okay, thank you very much. Do you hear me?
Yes, very well.
And do you see my screen?
Yes, everything is okay.
Okay, perfect. So, thank you so much. Good afternoon, good evening, and good morning also, everybody. At first, I would like to thank the organizers for giving me an opportunity to present this work here. And well, Victoria is a very, very beautiful city. This is a place that I came to, the first place that I came to after São Carlos and São José do Rio Preto in the year 2014, 8 years ago. And when I was there first time in 2014, I was just, wow, what a beautiful city. And for me, at that time, Victoria is a city that, for me, I just saw in movie in my life before. It's very, very beautiful. And after that, the second time I was there in the year 2019 for the the first meeting on foliation and singularities. And I do have a lot of good memories about Victoria. So I regret that I cannot be there in person this time. And I hope that next time I can be there in person. So now allow me to present the work here. And as presented, I will talk about a proof of the Euler-Poincaré formula using the Cauchy method for some surfaces. And it is a great pleasure to say that it's a joint work with Professor John from Brazil. And the idea of the work came from a course that we had together in a course for the student in University UNESP in São José do Rio Preto in the year 2016 when Professor John from Brazil was there as visiting professor. He was there 1 year as visiting professor. And in the year 2016, in the occasion that he was there, we gave together a course for students in an event called the Week of Singularities, and in Portuguese is A Semana da Matemática. This is an event that our Department of Mathematics in São José do Rio Preto, we organize every year. And in this year, 2016, Professor John Parasile and myself, we gave a course about the Euler-Poincaré formula for students. And in this course, we explain about the Cauchy proof for the Euler formula. And the idea came because we asked ourselves why the Cauchy proof does not work, and why there are some counter examples for some particular cases. And then we try to understand. We try to understand the counter examples, and we try to resolve to solve the problem. And this can work here. So let's recall that the Euler formula says that for any convex polyhedron, then this is the number of vertices minus the number of edges plus the number of faces of the given convex polyhedron is always equal to 2. And the name Euler formula came the first time in the year 1750. And only 61 years after, Cauchy gave the first combinatorial and topological proof of Euler formula. And this is a very, very nice proof. I will present you later on. And in this proof, Cauchy used only a planar representation of polyhedra and 2 operations called Cauchy's operations that are very, very beautiful and very accessible. I will present you later on too. However, there are many, many controversies around this proof. For example, in this paper, we can find that the mathematician Lacato and mathematician Elon Lima, they provide counterexample to the Cauchy proof, and they show that Cauchy proof does not work in some particular cases. Nowadays, you can see in this site of F. he updates on the proofs of the Euler formula, and there are 20 different proofs. However, in this proof, they use tools appeared later on Cauchy's time. And the purpose of this talk that we prove that in fact the proof of Cauchy works, but to do that we have to define a lifting technique, and with this lifting we will define a suitable subtriangulations so that the proof of Cauchy work for proving the Euler formula. And after that, as applications, we prove also that the Cauchy proof work also for the torus, projective plane, and the Klein-Bro too, and even for the pinch torus with the singular variety. So I'm so sorry that my talk is not really about singularities. It is more about topology, but we will mention anyway about pinch torus, which is a singular variety. So I'm sorry. Okay, so now in this work to prove the Euler formula, we are going to prove this theorem saying that if we have a triangulated polygon in the plane homomorphic to a disk, then the Euler characteristic of the triangulated polygon is equal to the Euler characteristic on the boundary plus 1. Why? Well, if you have this theorem, then we have the Euler formula. So let me borrow the idea of Cauchy for the explanation. So the idea of Cauchy is the following. You take a convex polyhedron, and as a zone, you remove this face P on the convex polyhedron. And the idea of Cauchy is we contrast a planar representation of the polyhedron after removing this phase. And according Glagato, he said that it's like you put a camera over the face removed, and then the planar representation will appear as a photograph, something like this. Okay, and on this planar representation, because we are working with convex polyhedron, then you don't have any identifications on the boundary. So the Euler characteristic on the boundary is equal to 0. So if you use the theorem, you have the Euler characteristic of your planar representation here is equal to 1. But don't forget the removed phase at the beginning. So you have 2 for the Euler formula. So if we can prove the theorem using just the method of Cauchy, then we can prove the Euler formula using just the method of Cauchy. But in this work, we prove the theorem, which is a stronger tool for proving the Euler formula. Why? Because as you see here, with convex polyhedra, you don't have any identifications on the boundary. And this theorem we prove for any triangulated polygon with possible identifications of simplicities on the boundary. This is the reason why is the application. After that, we show that our method can be applied also for surfaces such as torus of any genus, and the surfaces that are non-orientable like a projective plane and Klein-Broto, and even for singular variety pinch torus. So from on now, we focus on this theorem, and we prove it using just 3 things. The first one is a lifting technique. The second one is the use of subtriangulations. And the third one is the Cauchy's method. Let us remark that we know very well that there are a lot of modern and fast to prove the theorem, but in this proof, they use tools very deep in topology, appear after Cauchy time. And in this work, we prove the theorem using just the Cauchy method. But to do that, we need to use a lifting technique, and we define a suitable subtriangulation. So let's go to our proof of this theorem using Cauchy's method. So for the top B compact, I will not explain you what is the Cauchy method here, but I will explain you where we use Cauchy method during our proof. So let's recall that what we want to do. So we have a triangulated polygon homomorphic to a disc. We want to prove that the Euler characteristic of this given triangulated polygon is equal to Euler characteristics on the boundary plus 1. So here is our triangulated polygon, and the boundary is the red one that I draw here. Okay. So the proof of the theorem consists in 4 steps. The step 1, we will lift the triangulated polygon into a pyramidal shape. To do that, at first, we assume that the origin of the plane is inside of a simplex sigma 0 in the interior of the polygon like this. This simplex is the organ to 1 here. Okay. Now we consider the Euclidean method in R2, and we assume that the distance from the origin to all the vertices of our polygon are different. Otherwise, we can use perturbation and our proof will not change. And we denote by A1, A2, A3, the vertices of this simplex sigma 0. And we denote by V1, V2, and so on, Vk, the vertices of the boundary. And for the other vertices of the polygon, we denote Y1 is the one which is nearest to the origin. And for the others, we denote them with the increasing order of distance from 0. For example, here, Y1 is far than Y1. Distance from 0 to Y1 is the smallest, and after that we put Y1 is the second, that's a near from 0, and like this you put Y1 and so on Yn with the increased order of distance from the origin. Okay, so now we will leave this term, this polygon to a pyramid like this. So what do? First of all, we fix the boundary in the horizontal plane, the plane, and we leave this triangle, the organ to 1, to the plane P0. P0 here is horizontal plane. It has the distance n plus 1 with the respect to the base plane. And we leave the vertices of this triangle to U1, U2, U3 in such a way that U1, U2, U3 are orthogonal projection of the vertices of this triangle in the plane P0. Okay? And for the other vertices, we will leave them like this. For example, S1, you leave it in the plane P1. P1 here is a horizontal plane that is parallel to P0 and have a distance 1 unit with respect to P0. And like this, you leave on n vertices Y1, Y2, or Yn here in the polygon. Okay, so you leave on the vertices of the polygon, and like this you have a pyramid like this. Okay, and it is clear that the triangulation on our given polygon induce a triangulation on the pyramid. Now in the step 2, we want to contrast a sub-triangulation from the old triangulation that we have already here. So to do that, we do in 2 steps. Step 1, you see that here, for example, this H intercept the plane P1 as one point here. So we define is new vertex for the new triangle. Here we say that for our new decomposition. Okay, so like this you have new vertices, and like this you have also new edges. And in this step we do not change the Euler number because we add the same vertices and the same edges. But in this step we have only a decomposition. We do not have yet a triangulation because, for example, you see that this pink one, is quadrilateral. It's not a triangle. So to have a triangulation, we continue to divide each quadrilateral into 2 triangles like this. And in this step, we do not change the Euler number too, because we add one edge, and we add more one triangle. So we do not change the Euler number. And like this, we get a subtriangulation on the pyramid. And like what we did, we do not change the Euler number. So the Euler characteristic of the subtriangulation on the pyramid is equal to the Euler characteristic of our given polygon at the beginning here. Okay, so from now on, we will work on the subtriangulation on the pyramid, and we will prove that the Euler characteristics of this subtriangulation is equal to the Euler characteristic on its boundary in the base plane plus 1. But to do that, we need this step 3. This step is a very important step. It's the important point in our proof. So that the Cauchy method works, that we will prove that its horizontal plane intersect our pyramid, which is a curve here, and this curve is homomorphic to a circle. Okay, so to prove this, first as on, we make a projection of the subtriangulation on the pyramid to the plane base, and you get something like this. And we say that this projection, we mean orthogonal projection, and this projection gives us a subtriangulation of the given polygon, because by construction we don't have vertical edges. So it's clear that as you have a subtriangulation on the pyramid, so you have also a subtriangulation of the given triangulation here. Okay, so now we prove each level curve here is homomorphic to a circle by induction. In the level P0 here, it's clear because the intersection is the boundary of the triangle U1, U2, U3 here. So it's clear that in this case, the intersection is homomorphic to a circle. And now we assume that in one level B PI here, the curve is homomorphic to a circle, but in the consecutive plane, the level curve is not homomorphic to a circle. So it has happened that in the plane PI plus 1 here, we have this point is the multiple point, but it's not possible because if you have the point as a multiple point, so when you take the projection to the base plane, so it appears also somewhere here multiple point, and in this situation, this edge is a common edge of 3 triangles. But we prove that by projection here you have a triangulation, so this case cannot happen. So we finish to prove that each level curve of each horizontal plane with the subtriangulation on the pyramid is homomorphic to a curve. Okay. So now we go to our final step of the proof. We will prove now that the Euler number of our given triangulations is equal to the Euler number of the boundary plus 1. But as we saw that with our subtriangulation, the Euler number of this pyramid is equal to the Euler characteristic of our given triangulation. So we will work on this pyramid. So the idea is that at first we will remove a triangle U1, U2, U3 here. We remove it. We remove just the interior of the triangle, okay? And after that, we will prove that we can remove all the triangle situated between two level curves without changing our Euler number. And we prove that we can do that until we reach the boundary. And when you reach the boundary, because our process does not change the Euler number, then when you reach the boundary, you have the Euler characteristic is equal to the Euler characteristic of the boundary. But don't forget the triangle that you remove at the beginning. So we get the theorem. Okay. So let's do that. So in this step, what do we need to do? We need to prove that we can remove all the triangles situated between two consecutive level curves without changing the Euler number. So here we chart two situations possible that can happen about the triangles situated between two level curves here. Okay, and I choose here the second case to explain you how we remove all the triangles situated between two level curves here. So let's go. The idea is like this. We assume that we can remove already all the triangles situated before. So you have here is a hole in blue. So the idea is we remove step by step all the triangles from the left to the right to extend the hole. So first as shown, we remove this triangle alpha 0, alpha 1, beta 0 to extend the hole. So in this case, you have to remove one edge. This is alpha 0, alpha 1, and one triangle, the pink one, like this. Like this, you remove, you extend the hole in blue. Okay, you see? So we remove one edge and one triangle, and you extend the hole in blue. So in this operation that you remove one edge and one triangle, you do not change the Euler number. And this operation called operation 1 in the Cauchy proof. Okay, and now we continue. You have to remove this triangle beta 0, alpha 1, alpha 2. And in this case, it's different from the first one. This case, you have to remove two edges, one vertex, and one triangle to extend the hole. You see? So in this case, you remove one vertex, two edges, and one triangle. So you do not change the Euler number. Okay? And this removal that you remove one vertex, two edges, and one triangle is called the operation 2 in the proof of Cauchy. And we prove that we can use these operations 1 and 2 of Cauchy, and we can remove all the triangle from the left to the right situated between two level curves until this curve, and you continue like this until the boundary. So we get our theorem. So we have some remarks here. Remark 1, in the proof above that we have just presented you, we take the identifications of symmetries on the boundary in account. Remark 2, given a triangulation key of the polygon, the group does not depend on the choice made. And the remark 3, the process in the set draw here, that we use two operations, 1 and 2. So the two operations 1 and 2 are exactly the Cauchy's operations in the Cauchy proof. So now we go to Cauchy proof and controversies. So as at the beginning, I introduced you already a little bit that the idea of Cauchy is that you have a convex polyhedron. First as on, Cauchy remove a face P on the convex polyhedron, and after that he construct a planar representation associated to this polyhedron after removing this face P. So it's like you put a camera over the face that you remove, and then the planar representation appear as the photograph. So something like in this paper, and after that we get a triangulation of the planar representation. And because of the remove face, we have a hole in blue appear around our planar representation here. Okay, and the idea of Cauchy is he say that you can use the operation 1 and operation 2 to extend the hole in blue until you reach just one triangle. Okay, for example, here you see that to extend the hole, you remove one edge and one triangle. So here we use the operation 1 and you extend the hole blue. And here to extend the hole, you remove two edges, one vertex and one triangle. And like this, the hole is extended until you reach one triangle, and on the left triangle, the Euler characteristic is equal to 1. And you don't forget the face that you remove at the beginning. So you get 2 for the Euler characteristic for a polyhedra. Okay? But Cauchy said that to do that, we have to take care of keeping the boundary homeomorphic to a circle. We remove the triangles using operation 1 and 2, but we have to take care that the boundary is always homeomorphic to a circle. But the problem is how to take care of keeping the boundary homeomorphic to a circle. And for our knowledge, until nowadays, this question has not been verified by only Cauchy's method. For example, some counter example of Professor Aaron Lima. For example, in this case, the hole is in blue. So to extend the hole, in this case, you have to remove two edges and one triangle. So the Euler number changes. And in this case, to extend the hole, you need to remove three edges, one triangle. So the Euler number changed. And in this case, to remove the hole, you need to remove one vertex, three edges and one triangle. So the Euler number changed also. And in this case, the boundary of the hole is not homeomorphic to a circle, and you have multiple points. So why with Cauchy's method our proof works? Because the point important in our proof is that we construct a suitable triangulation such that each level curve here is homeomorphic to a circle. So when we take the projection, so you see each level curve here is homomorphic to a circle. So we can remove all the triangles using just the operations of Cauchy, keeping the boundary homomorphic always to a circle. And like this, we solve the problem of in the proof of Cauchy. Okay. And its applications is we use the Cauchy method to prove this theorem. And this theorem, in this theorem, we take in account also the possible identifications of simplices on the boundary. So the Cauchy method in our work also for the torus of any genus, and even for some surfaces that are non-orientable is projective plane and Clapeyron, and also for a singularity intertorus. So that's all my talk. So thank you very much for your listening and attention. Muito obrigada, muchas gracias, and cảm ơn các bạn rất nhiều.
Thank you very much, Thuy. Questions from the audience? From the people online? Well, if there are no questions, let's thank Thuy again. Thank you very much, Thuy. And we have a coffee break now, and we continue at 10 to 4. To 5, sorry.
Bonsoir, on n'entend pas. On n'entend pas. Peut-être tu as un problème avec le micro. Maintenant, on t'entend, mais c'est très faible.
Ok. Je voulais te féliciter à la fin de ton exposé, mais mon micro ne marchait plus.
Ah, pas de problème. Pas de problème.
Alors, je dis bravo maintenant.
Merci.
Bravo. C'était très bien. Super, très bien.
Merci.
Et je trouve très bien l'idée de mettre, d'expliquer Cauchy après, et pas avant. Ça, c'est bien. L'idée
Oui, mais
d'expliquer les opérations de Cauchy après, ça, c'est très bien, très bien.
oui, merci.
Très bonne idée.
Je pense que c'est bon aussi d'expliquer le Cauchy avant, parce que sinon les gens se posent toujours la question, mais qu'est-ce que c'est Cauchy, la méthode de Cauchy, n'est-ce pas? Mais ça c'est un peu pour le mystère, n'est-ce pas?
Très bien, très bonne idée. Bravo.
Mystère.
Bravo. Mais je ne sais pas pourquoi mon micro, juste à la fin, quand j'ai voulu le mettre, impossible. Bon, c'est l'informatique. Les problèmes d'informatique. Très bien, bravo.
Merci beaucoup. Olá, boa tarde.
Boa tarde, Josefa. Você quer
Oi,
apresentar,
boa tarde. Não estou
apresentar
ouvindo.
para olhar se todo dá certo?
Desculpa, não
Sim.
estou ouvindo bem.
Pode apresentar sua palestra para ver se todo dá certo?
Uhum. Consegue ver e me ouvir?
Tudo bem, obrigado. Our last speaker of this afternoon is Josefa Genyle do Nascimento Santana from UEPB, Brazil. And she's going to talk about projective structures with Fuchsian-type singularities.
Thank you very much for the event organization, for the nice opportunity to talk here. In this talk, my goal is to show a characterization, the monodromy of projective structure with Fuchsian-type singularities, namely any representation from the fundamental group of a Riemann surface of finite type in PSL2C can be represented as the holonomy of brushed projective structure with Fuchsian-type singularities. In the end, I explored the problem of minimized angles in these projective structures. These are the results of my doctoral thesis defended in 2020 at Universidade Federal Fluminense. In the first moment, in the introduction, I will show the problems that gave origin to this work. After, I will introduce the main concepts that I use several times during this talk as a Riemann surface of finite type. In particular, the projective structures with Fuchsian-type singularities. I will present the main result of the extents of the projective structures with these singularities. And in the end, I will obtain the formulas that relate topological invariants to the surface and analytical invariants to the foliation of the fiber bundle in the condition for the representation that do not minimize excessive angles to the projective structures. So, Galo, Kapovich, Marden in 2000 proposed this problem about a natural question about complex projective structures, and the monodromy representation is to describe which representations can be realized as monodromy of projective structures. So we have this problem here, prove and explore the extents and non-uniqueness of complex projective structures with given monodromy in punctured surface. In the closed surface, Galo, Kapovich, Marden proved in the paper said exactly which are the representations in surface as closed surface with the genus at least two can be represented as a monodromy of complex projective structures without singularities. So here, the representation rule is monodromy of complex projective structures as if only if rho lifts to SL2C and rho is non-elementary. For the case that rho doesn't lift to SL2C, it's necessary just a single brush point to realize this structure projective. So we have the other problem, the problem to make precise and optimize the connection between brush divisor and the monodrome. Namely, compute this function here in the D by the homomorphisms, the fundamental group of S in PSL2C to the Z, where d rho is the smallest integer for which there exists a brushed complex, a brushed projective structure with brush divisor, degree D, and monodromy Rho. In GKM, Gal Cabo-Vitimar, they've showed the brush order is 0 for all non-elementary representation and lift to SL2C, and 1 for all the other cases. So we have these concepts that use here. We define a Riemann surface as a topological surface with a complex structure, and we say that a Riemann surface of finite type if it is biolomorphic to S star, where S is a compact surface and P is equal to P1 until Pk, a finite subset of S. We call this Pi of the cusps. We have this first definition for complex projective structures with an atlas, such that the maps are over CP1, the Riemann, to CP1, the Riemann sphere, where the transition maps are restriction of Möbius transformations. We have this second definition here. We denote S tilde is a universal covering of S, and we define a complex projective structure on S by a pair, the developing map dev and Rho, the monodromy representation, that dev and Rho, dev is equivariant with respect to this monodromy representation Rho. We have this identity here. We say true. Projective structures on S are equivalent with the developed maps differed by an homography. So we have the third definition that uses sections or CPU bundles. We define here a suspension with the product we define the suspension of the representation Rho. We take the product S tilde times Riemann sphere by this and define this equivalence relation. We take two pair, and in the first coordinate, I relate by the action by the fundamental group, and the second coordinate, I use the action by the monodromy. So the map, this map here with the product, we use the pi is the covering map of S, since it's invariant by the equivalency relation, and it induces a global submesh pi, and this define a holomorphic CPU bundle of S. So the foliation defined by the W equal constant is preserved by this action and defines a transversal foliation F for all CPU fibers on. So use the description about the structures projective as a trap. I have the theorem by Goldman, who is a representation. There is a natural bijection between CPU bundles with monodromy Rho in S on this section, and the sections of the fiber bundle, this suspension here, transaction to the foliation F. So we define two, a singular projective structure in S as a complex projective structure in S star, where S star is S minus P1, Pk, where P1 and Pk is a finite subset of S, and each Pi is called the singularity of the structures. So the monodromy local, or such there is the monodromy of a singularity in the monodromy of the restriction of projective structure to a disk around it. So we have this example here. We take in the Riemann sphere, we minus 0 and the infinite point. with the non-trivial monodromy, we can build a projective cards as the brush of the multivalued map Z alpha, that the alpha is a complex number minus no integer, and the monodromy around the cusps conjugate to multiply by exponential 2 pi I alpha, and you have the brush of logarithm Z plus Z minus N is defined singular projective structure with this monodromy by a translation. So we are motivated to define these singularities, a singularity of Fuchsian-type, as a point such that we have a map up to local holomorphic coordinate change is given by Z alpha or logarithm Z plus Z minus N. So we define now a singular projective structure is of Fuchsian-type if all its singularities are Fuchsian-type. So these definitions here generalize brushed projective structures or spherical projective structures. And so we proved the theory, extensive theory of projective structures of Fuchsian-type. This theorem answers the first part of the problem that I announced here. I obtain a result analogous to the Galois-Kaplowitz-Arden for the Riemann surface of finite type. So here we have S, a compact Riemann surface of n genus, and P1 until Pk a finite subset in S, where we write S minus S star equals to this subset here, given a representation ρ by the fundamental group of S star in PSL2C, there exists a singular projective structure of Fuchsian-type in S with monodromy ρ. So now we have a proof idea. We consider the suspension of the representation ρ into over S star when we take the compactification pi, use the local models chosen are, use the models that we have this recut foliation, and we can see that Brunella. In the case for the cusp with local monodromy non-parabolic, we have used this model here, and in the case parabolic, we use this, and the trivial monodromy, we use this model here for compactify. In the three cases, we have invariant fibers of defoliation over the cusps and one or two singularities of defoliation. And in each singularity, there exists a separatrix for it. After use algebraic geometry, we know that pi has at least one non-trivial holomorphic section sigma that is non-invariant by the Ricat foliation. After this compactification, we have Ricat foliation defined in the total space in the CP1 bundle. So after the cards of the structures projective can be calculated by the projection of the suction and along the leaves in the transversion file to the foliation. At the regular points on the surface, we will obtain up to appropriate coordinate change, complex projective cards, or Burson covers as Zn. So at the cusps, we obtain up to appropriate coordinate change, singular projective cards as a Z alpha, with the monodromy is, the local monodromy is non-parabolic. If the case with parabolic monodromy, we have these cards here. So with this idea, we prove the theory. So now we talk about the algebra geometric interpretation of projective structure with Fuchsian-type. Here, let pi be a CP1 bundle OVS associated to the monodromy representation Rho, defined fundamental group S time PSL2C of a projective structure of Fuchsian-type in S. This CP1 bundle is equipped with a Riccati foliation F Rho with the same monodromy obtained by compactified suspension of the representation Rho. The developing map of the projective structure on S defines a non-trivial holomorphic section sigma of pi non-invariant by F Rho. So under the above conditions, we can calculate this calculate the self-intersection of this section sigma S in P. We have this formula here. Here is the tangents order with the foliation F Rho if the section sigma plus Euler characters minus K0, where K0 represents the number of the fibers that are invariant by the foliation F Rho. These results generalize a formula by Gallo-Kapovich-Marder over surfaces without cuspes, the closed case. So now in the case we have K0 equals to 0. So the formula here, the order tangents, is equal to the degree of the brush divisor of the projective structure. So now we talk, we start to talk the problem of minimize the degree of brush or divisor. We have P, a singular point of the structure projective sigma with given monodromy Rho, and it's a consequence of the proof, the extensive theory, the Cauchy positive, the projective cards around P is equal to Z alpha plus NP. We have these restrictions here in alpha about the real part, or logarithm Z plus Z minus NP. We say NP is the brush order of sigma at P, and the sum here we define as the brush order of sigma. We define the Rho as the Rho in the second problem equals to minimal as sigma, where this sigma is a projective structure of Fuchsian-type with monodromy Rho. And you remark these NPs are the tangents or the foliation with the section in the minimal compactification. It's a consequence with the problem of the extensive theory. We define the foliation F Rho minimal that we choose the following local models to compactify. The same that I used before, as can see that Brunella. So this formula here, we have this restriction in the complex number alpha with the case non-parabolic, with the case parabolic, and with the case with trivial monodromy. So we have this consequence that E sigma is equal to or tangents the foliation, this foliation and the section sigma, and this E sigma equals to 0 if and only if the section sigma is transversal to the F minimum Rho. And we call F Rho minimum of the minimal compactification. Here, the compactification is considered minimal in the sense that the index in the singular points are minimal, and the second Stiefel-Whitney class is well defined. So we proved this theorem about the representations that cannot be represented as projective structures of Fuchsian-type without excess angles. So we have a representation here, rho by PS P1 S time, PSL2C, a projective structure of Fuchsian-type with monodromy rho has an odd brush odd if only if at the minimal compactification the second Stifel-Whitney class is even and the number of the cusps with non-trivial local monodromy is odd, or we have the second Stifel-Whitney class odd and the number of the cusps of non-trivial local monodromy is even. So for this case, we have the whole at least one, because here we have odd brush or the odd, so we have this condition here. So we can rewrite the second problem giving a representation rho by from the fundamental group of S-time PSL2C. What is the minimum brush on of the projective structure of Fuchsian-type with this monodromy representation? For the case, for this theorem, do you have, in fact, d rho equals to 1? And the other case, out the case of the theorem, do we have d rho equals to 0? So this problem is open yet, just a final comment. Gupta in 2009, indefinite, also proved analogous to the Galo-Kapovich-Marden theorem, where he used all the techniques provide 3D hyperbolic geometry, and also with Farad, they obtain a necessary sufficient condition for to represent monodromy as meromorphic projective structure. But I think the problem of minimize of the sum excess angles is open yet. So we have here this reference, use the models with recap foliation by Brunella. The article here is over the problems that motivate this work. And in this preprint here, there are these theories that I talk today, and there is also a discussion about the geometry and the topology of the Fuchsian-type singularities for to treat the problem of the non-uniqueness of the projective structures on Riemann surface of finite type. So I'm finished here. Thank you very much.
Thank you very much for the talk. Are there any questions from the audience? You have the microphone.
I have two questions. First of all, do you know any connections between Fuchsian projective structures and Fuchsian systems of linear differential equations? Also,
yes. The solutions with the Fuchsian, we have the equations by Fuchs, the quotient of the solutions, they are the same. We have two linear independent solutions. The quotient is possible to find the same cards. The relation is this.
Okay, and so it works in both directions. So I guess from Fuchsian systems, then you can build a Fuchsian projective structure. Yes.
Yes.
Yes. Okay. And then related to this, so my second question. So has anybody looked at higher dimensions? Namely, you consider not CP1 bundle, but you consider CPN. Yes, and you consider
No, not yet. I think it's a good question, but I didn't think now about with this 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 dimension.
Okay, yeah, I can tell you also why it all what I'm thinking about that when you're talking about automorphism of CP1, these are roughly 2x2 matrices, and the problem of realizability of a structure, that's all your main theorem, it says that when you're dealing with 2x2 representation, yes, you can realize any monodromy representation. It reminds like a theorem from Fuchsian systems that in 2x2, in dimension 2, for 2x2 matrices, you can realize any monodromy representation by a Fuchsian system. But as you probably know, in higher dimension, this fails. So there is a counterexample of Bollybrook saying it's something from dimension 4. Already not all monodromy representations are realizable. So it's interesting to see whether this parallel indeed. So if you consider projective structures in higher dimension, whether you will get also some counterexample. Yes, since there, as you say, there is a connection.
Okay, thank you.
Are there any more questions from the audience in online? Well, if not, let's thank the speaker again.
Thank you.
And please don't go before, well, this is the last talk of the event. The last one was canceled. So, well, I would like to first to ask you to make a big round of applause for the organizers. They think they make a very good job organizing this hybrid conference, and also to the scientific committee for the wonderful program. And also, we want to thank all the staff who helped us to do all the technical details behind the organization. So please, let's thank them. Everything was possible because of them and many others. Please, thank you very much. And we hope to see you in the next one in Mexico.
Gina, do you want to say a few words? She's not there anymore, I guess. So thank you for coming and for the very nice questions and the participation with good talks and nice talks. And so, well, we quit now, okay? If someone wants to say something, feel free.
Oh, of course, we thank a lot organizers, because it's not easy to organize such a meeting. We also presentially and also by the web. So I say bravo for the organizers. And I hope next time we will meet all together in Victoria, or I don't know where will be the next one. I propose an island which is a 3-person island in in Pacific, which is near Mexico, near not near Brazil, but Chile. I don't know. The 3-person island is in Europa and completely lost. And why not there? Bravo for the organizers and hoping to see everybody present.
Okay, thank you, Professor. See you next time.
Oh.
Muito obrigado a todos. Un abrazo para todos. Hasta pronto.
Abrazos. Chao. Chao.